Now?
Let me, no.
It looks better.
Looks better.
Yes. There were 3 microphones, so
But I'm still here myself.
here?
It's not so worse as before, but every time we talk, we hear a background sound.
Okay. My microphone. Yes, maybe.
No.
If I reduce a little bit the sound of the speakers, I don't know how I can do that,
Okay. No, but I think now it's solved. A little bit.
Yes. So
It looks fine, I think.
Now it's fine.
it's fine?
Yeah.
Yeah.
Okay. Yes. Like this?
I think it's fine.
Yes, for me it's okay.
Yeah.
Okay. We just have to wait for a few minutes for the rest of the jury and my supervisors to come. But I see them coming now, so... Hello, Panagiotis. George Simonar, how are you? Καλά, πολύ καλά. Ο George είναι πάνω. Ο George είναι πάνω. Ναι, okay. There is a little bit of echo for the jury. Ricardo and Francois, they heard a little bit of themselves when they speak. So I don't know if it's the mic or if we can go a little bit down with the sound of... No? Okay.
So I don't know if everyone is in the room. I see that online all the members of the jury are there. So Konstantinos, can you tell me if the members of the jury physically present are all there?
We are still waiting for a few minutes for George Karinotakis and Simon Kamal to come.
Okay.
As well as Anna Busic. I think they are all together at George's office, so they will come in a few minutes.
Okay, then tell me when they enter, because I will share the jury so that I can start to make the presentation.
Okay. I'll inform you. Thank you.
Thank you.
Hello. Nice to meet you, Konstantinos. Hi, Simon. Everything good? So, everyone has arrived. I don't know if you can hear me.
Yes. So then we can start. So good afternoon, everyone. So it's my pleasure to share and introduce this PhD defense of Konstantinos PARGINOS. The work of Konstantinos was dedicated to advanced methods for enhancing the interpretability of AI tools in the energy sector. And the jury for evaluating this thesis is composed of the following members. So we have Professor Spiros Katsivitsilaidis from the University of Denmark, Professor Alfredo Vaccaro from the University of Sagno, myself, François Vallée, professor at the University of Mons. The three of us were acting as rapporteurs of this thesis. And then on place, physically present, we have Dr. Anna Buzic. We have Panagiotis Padapoulos from University of Manchester that works as examinator of this thesis. And then we have the three directors of the thesis. So Simon Kamal, Ricardo Bessa, and George Karignotakis. And so we will first start the session by a presentation of Konstantinos that will last for about 40 minutes, 40 to 45 minutes. And then we will move on to the Q&A session with the different members of the jury. So Konstantinos, if you are ready, the floor is yours for your presentation.
I would like to thank you for the introduction, and I would like to thank the jury and everyone being here for this PhD defense. So my PhD is supervised by George Karignotakis, Ricardo Bessa, and Simon Kamal, and the focus of this research is on advanced methods for enhancing the interpretability of AI tools in the energy sector. The outline of this presentation will be an introduction, an intro into the foundations of interpretability, symbolic and causal learning, as well as the conclusion and perspectives. And on the top right of each slide, you will be able to follow this outline throughout the presentation. So, what are the challenges that motivate us to use AI tools in the energy sector? First of all, we're experiencing a vast data explosion from smart grids, Internet of Things devices, and sensors that we require some intelligence analysis in order to extract useful information out of them. Then there is an increasing complexity in the energy systems, given that they are more decentralized with renewable energy sources, storage, and all this to be merged with traditional grids. And finally, the speed of decision making is increasing and is coming closer and closer to real-time decision making. So, efficient models are needed in order to handle this massive data, to perform fast and complex decision making. And some of the applications in the energy sector that they could benefit of such models are demand and rest forecast, predictive maintenance, as well as anomaly detection, and much more. In this direction, artificial intelligence offers the potential to address these challenges. On the other hand, we should note that artificial intelligence itself has its own challenges. So, in general, it's characterized by difficulty to assess the outputs of high-dimensional and non-linear models. And the goal and objective of this thesis is to move towards something that is more understandable, something that we can correlate and identify the causal links of the outputs towards the inputs. And in general, to satisfy the industrial requirement, the industrial need of the ability to explain or to present a model output in understandable terms to a human. On top of that, on top of the industrial requirements, there is an ongoing pressure from regulatory frameworks. European AI Act precisely characterizes the energy system as critical or high risk, let's say, system in the framework of minimal to unacceptable risks. And this is due to the critical to the critical, let's say, role that they play in our social structure, that if we experience a failure in power grid, then we have huge collapses, as recently noted in Spain, France, and Portugal. Thus, to comply with this conformity assessment, there are some compliance costs. We have conducted a study in order to calculate those costs in a regional level in Switzerland, as well as Austria and Greece. And here we have to highlight that human oversight over AI system outcomes and safety verification costs are 2 out of the 5 that somehow can be treated if interpretability and trustworthiness are included into those tools. In order now to comply, to balance those compliance costs, we have identified with this cost breakdown that a profit growth of 10% is essential. To summarize all those 3 parameters, the overarching objective of this thesis is to develop and elevate the effectiveness of power system operation methods through novel interpretable AI tools. We should focus on the following application. So, given the title of the thesis that it's in energy sector in general, we need to tackle some case studies for transition system operators, for market trading, and for distribution system operators. So we have some adequacy studies for the TSOs, the day-ahead energy market trading case study, and overloading lines for the distribution system operators. The requirements to achieve this objective is to simplify complex modeling chains, to increase the transparency, maintain or even improve the economic benefits, and consider the regulatory frameworks. Thus, in general, the methodology followed starts with design of interpretable models, which are either post hoc or ad hoc, and we are going to focus on those definitions later on the foundation section, to elevate their performance in typical power system applications, and to assess these implications of different legal frameworks in Europe, US, and China. Now, to better understand the foundations of interpretability in the energy sector, first we need to start with the definitions. And what's more problematic than a field which is not well defined? There is a contradicting literature between the terms explainable, interpretable. Some of them clearly differentiate between them. Some of them use them interchangeably, and this can create some confusion. Thus, we are proposing, and following this slide in the rest of my thesis, we are proposing to clearly differentiate between the two. We split with interpretable AI as ad hoc inherently interpretable solutions and explainable AI as post hoc tools. So a tool that it's, let's say, added on a modeling chain on top of an existing black box tool. So to start with ad hoc, we can see that the model receives a different type of input data. It's characterized by transparent inner mechanics, so we can clearly understand how it makes its decision. And then the output also facilitates reasoning. Whereas when we are using a black box, we don't have this aspect of reasoning directly as an output of the model. Whereas when we insert the input data and the output data of the black box into an additional tool, then we can also achieve both those aspects that we are looking at. To have a better understanding of those details, we need to answer the question of which features or attributes are important to the model, thus introducing the concept of feature importance. And how do those features interact to obtain the target variable? So introducing the rule-based. Sorry. For the feature importance, a clear example is the weights that affect, let's say, the different variable, the sensitivity of the output, different variables into simple linear regression model. Whereas for the rule base, we can look at a decision tree that instead of just observing the yes or no output of a model, let's say, that can help us decide whether to bid or not to bid into a specific electricity market under certain conditions, we can clearly understand and define which parameters led us to take those decisions. For the post hoc feature importance, when we don't have inherently, let's say, built in those properties into our model, we are trying to approximate them. So we are looking at some either matrices or some arrays of of the weights that affect the different variables, that they are either reverse or directly correlate to the output. A simple example is that SAP and LIME method, which are the two most widely used method both in academics and into practitioners, that they are looking on how to explain something that's produced by a complex AI tool, which come with some advantages and some drawbacks. The advantages of having those post hoc feature importance method is that we can create local surrogate models that explicitly can help us in understanding which features contributed the most in the output of this model, both for local and global feature importance. But some of the drawbacks are that they increase the modeling chain as they are an addition to the already complex model. SAP is computationally expensive, and feature importance in general is not an actionable explanation. What do I mean by an actionable explanation? We define that as an explanation that shows how to modify the features in order to affect the outcome. To better understand those actionable, let's say, information, those actionable explanations, we can look at this toy example that we performed on the use case of scarcity events analysis based on the studies of NSOE, of the European Network of Transmission System Operators data, in order to understand whether we are going to have scarcity events, so expected energy not served, in certain regions of our grid. And the result, by using one post hoc tool called CN2 rule-based model, is that we can create and we can, let's say, derive some simple rules that they are even naive, let's say, even some bachelor students can, they already know that, for example, if the generation is low and the load is high, then the risk of having imbalance is high. The interesting thing here is that this was data-driven, so this was not, let's say, explicitly defined by an expert, a human expert, in order to set this rule. This was derived by the data, and also it's an actionable explanation. Why? Because you know that when you are approaching this scenario, when you are approaching this imbalance scenario, you have either to increase the generation or to reduce the load. Some of the drawbacks are that, especially for scarcity events analysis, is that it requires a large and representative data set in order to generate some accurate rules. And due to the limitation of not that widespread, let's say, events of blackouts. Now, I mean, there was one recently happened, and all the news started to speak about that. So we don't have a lot of data points, a lot of data sets on expected energy not served scenarios. So we have limited, noisy, or even biased models. Now that we have clearly defined between the two, between interpretable and explainable tool, how are we going to select between the two? The first step is to ask ourselves how important is interpretability relatively to predictive accuracy. If it's not important, we can use any model. If it's very important, we should use inherently interpretable models. The interesting part starts in this gray zone that you don't know if you are seeking only interpretability or only predictive accuracy. So we say that it's somewhat important, and we need to ask ourselves, is a complex model performing better than interpretable one? If the answer is no, then there is no reason to go for complex models. You can just use the easy to understand that facilitates reasoning. If the answer is yes, so you have a tool that it's overperforming an interpretable alternative, then you should go into post hoc methods, depending on what you are looking at. Are you interested into the decision understanding or into the model description? If you're interested to understand how the decisions are made, then you go to feature attribution methods, so post hoc attribution based methods, or if you are interested in the model description, you build some simplified surrogate model of that mimics and explains the complex, let's say, AI tool that you previously used. To conclude these foundations, let's say, section, we performed a binary segmentation between explainable and interpretable tools. There is a methodology for selecting between the two. We clearly define the discrete advantages from feature importance and rule-based methods, and we conclude by proposing a definition. In the end, we are not aiming either to build interpretable or either to build explainable models. Our need, the end user need, is to understand. Either it's an engineer, either it's an end user, either it's a policymaker, it's to understand how a model makes a decision. Thus, we propose this umbrella that covers both interpretable and explainable model, which is called an understandable AI. An AI system can be defined as understandable if its underlying model is inherently interpretable, ensuring fidelity by design, or if a non-interpretable model is augmented with an interpretable and accurate explanation. In the latter case, the system includes a post hoc explanation method to facilitate understanding. So in the rest of this thesis, we have moved away from just post hoc feature importance because the explanations are not actionable and often can create additional confusion. In this direction, we are looking at symbolic learning algorithms applied in power trading. The objectives of this chapter is to develop ad hoc inherently interpretable methods to enhance the following: human interpretability and controllability via the explanations that I previously defined, learning with less data and less computational effort via existing knowledge, and out-of-distribution generalization, for example, via reasoning, while combining the benefits that we previously said for feature importance and rule-based methods. Why we selected symbolic algorithms for that? Because they have a really interesting property. First of all, they create data-driven, simple analytical solution, but they have the ability to also optimize both the weights and the feature relations. Most of the optimization algorithms try to find ways to optimize the weights, whereas here we can also change the different operations between the variables. We can either have addition, division, subtraction, etc., which enables us to create the analytical solutions that we see over here due to the introduction of the grammatical space. So, as input, those models don't only receive time series data or let's say win production, price, whatever, let's say, data usually we include to the models, but also we can have a grammatical space that defines how those inputs, those features interact with each other. Those two are somehow producing the output that we see in this right-hand side of the graph, which in the example of bidding, let's say, the forecast of a wind power turbine, we can clearly separate and cluster the different wind speeds that we observe, receive an analytical expression for each one of those different areas. And as well, you can clearly see that instead of receiving just a number that will represent the megawatts that the model proposes us to bid, we receive an analytical expression that based on the current situation, we can make our decision or even enhance and change later on this expression. And this facilitates both receiving the correct megawatt by solving this, let's say, expression that we're going to bid, and the reasoning behind on how do we end up with this, let's say, number. So in this symbolic algorithms, let's say, context, usually symbolic regression is used, which is a post hoc method. What do I mean by that again is that we try to create surrogate model of the output of a black box or a tool that someone is using in order to receive, let's say, an optimal trading decision, and try to approximate it through those policies. The novelty of this study is that we are moving away from just an error minimization, and we are introducing a direct custom objective function within the training of the symbolic learning as we introduce this algorithm that fits our purpose, so fits the specific problem that we are looking at, and we can also add a specific complexity penalty metric to control the complexity or the non-complexity of those of those outputs, of those analytical expressions. How are we going to do that? First of all, we need to have an understanding on what a symbolic policy could look like. We saw the example of the wind turbine, but in a more theoretical and abstract way, there are tree-like structures, and those tree-like structures operate within a space of possible, let's say, expression and their parameters, which is derived by the input features and the operation grammar space that defines how those features interact with each other. So we initiate by randomly generating such initial populations that in the beginning they don't really have a specific structure, or they don't fit the purpose that we are looking at, but by introducing a reward function, we are training them, and our goal is to estimate the optimal policy by searching the space of those expressions that maximizes, let's say, this reward. Then we apply a selection mechanism. That means that we randomly take some samples and we rank the reward among them. So we select the best individual of each one of those random samples, and we perform reproduction to them. So what exactly is reproduction? Reproduction mechanisms include crossover and mutation, and this illustration helps us understand a little bit what we mean by that. Mutation is that we have a tree and we just cut part of this tree, and then if we do a crossover, we mean that we replace this part that we cut from one of those policies with another one. So by doing this iterative process, heuristically, we can either reach a specific fitness threshold, or we can reach a maximum numbers of generation and this processor output the best individual. Due to the nature of this iterative algorithm, it's extremely easy to integrate a human expert knowledge to it. And this is what we did in this case. A human expert can define key variables for clustering of this algorithm. It can update the grammatical space and also fine-tune the parameters. For example, if it sees that the policies are, for example, overfitting a specific purpose, we can change the rates of the crossover or the mutation in order to better explore the space of potential solutions. Now, for the practical case study, we looked at two renewable energy plants, a PV plant with a peak capacity of 16.32 kilowatt located in Porto at the premises of Inesc, and a wind plant comprised from 24 wind turbines located in Galicia, Spain. Then we took both of those datasets are open and available in order to facilitate reproduction of results. And the price data themselves, they are also obtained through the transparency platform from NSOE for a period that we believe that it's representative. It's from 2017 till 2022. And why do we say that it's representative? Because it included events in normal, let's say, prices before 2019. Then in 2019-20, we had the COVID crisis. So we experienced low prices. And then we also had the energy crisis that resulted into some higher prices. For each one of those periods then that we split it, we train our model following a typical train validation and testing. And in order to bridge the gap between this case study, between the trading problem and the symbolic learning algorithm, we need to start defining what we are looking at in terms of symbolic learning. So the optimal policy that we are looking at is the P offer. So what we are going to bid here. So what we are going to bid, let's say, to the market. How we are going to calculate that? By a reverse reward function. So by minimizing our cost. Instead of maximize the reward, we are minimizing our cost. And what is our cost? It's an imbalance cost in a dual price market scenario, which is defined by the difference between the actual generated energy and what we are going to offer to the market. Also times and dependent on the imbalance prices. The benchmark for performing such a trading, let's say, strategy or decision is by bidding the analytical quantile. The analytical quantile is a predictive inverse cumulative distribution function of the produced energy, which is dependent directly on the forecast of the imbalance penalty prices, on the predicted imbalance penalty prices. And then since we formulated this case study, we directly implement into the symbolic learning approach. And then we have the human expert, let's say, intervention part, which fine-tuned the model by conditioning, let's say, the training according to different price levels, according to either it's a global model, so it's a model that looks at all the data at once, or it splits the data hourly, because we see that according to different hours of the day, for example, solar has a different performance, so we might optimize our results like that, and or even by price spreads. And then on top of just a simple grammatical space, so including only basic operators like addition, subtraction, multiplication, and division, we also included an if then else, let's say, threshold function. And in order to better understand that, the enhanced grammatical space included the basic one, plus all these different, let's say, ways to check those thresholds between the variables that we are looking at. One example is that if the negative, let's say, imbalance price forecast is above the mean of the already observed imbalance penalty forecast, then you bid A, else you bid something else. And why we did that is that because by using a dynamic bidding strategy through imbalance price threshold, we reduce the dependency on imbalance price forecast. We have noted that imbalance price forecast is extremely difficult to be really accurate. Thus, we want to minimize and to reduce our dependency on that. The resulting policies are, as in the first illustration, straightforward analytical solution. So you can see that the basic grammatical space resulted into some power quantiles as a bidding solution, whereas with the enhanced one, we have conditioned decision based on the different imbalance prices. And by looking at the numerical results, it's important to note two key outcomes of this study. The first one is by using the basic grammatical space, we were not that happy with the results. Why? Because more or less we performed similar with bidding the point forecast, which is what most traders do. They just bid the point forecast. So nothing really interesting happened here. The benchmark of analytical quantile still outperformed those results. Whereas when the if then else functions were introduced, when we somehow searched with the enhanced grammatical space, we improved the performance over all price scenarios and over outperforming this analytical quantile. And that was consistent in normal, low, and high prices, both in solar and wind case studies. to go a step further, we wanted to evaluate the out-of-distribution performance. And what do I mean by that? Is that what will happen if we test a model that is trained on low prices into high price scenario, and normal to high, normal to low, etc. And it's interesting to see that there was a consistency of increased performance across different price scenarios. So our reference point here is the point forecast, which is 0, and here we see how much we improved over the point forecast. Here the analytical quantile in both solar and wind case studies, you see that it's approximately 15 to 20% increasing this minimization of imbalance prices, whereas every one of the solutions that they were trained in the enhanced grammatical space, regardless whether it was trained on high, normal or low scenarios, it outperformed it. So it's this is presented as an evidence that these models can be generalized for different market conditions. They are more flexible, let's say, to the price shifts, which can create conditions for transfer learning across electricity markets. So the key contributions of this part of the thesis was the introduction of a novel symbolic learning method, which is directly ad hoc, that it ranks expressions using a cost and complexity penalty, thus improves interpretability. It incorporates the expert feedback to guide the search and the grammar space. It demonstrates interpretable trading strategies for the renewable energy sources in day-ahead electricity markets, and it uses a dynamic bidding, which is more adaptive than static quantile methods. Finally, numerically speaking, we saw up to 50% reduction in balance costs when the enhanced grammatical space was introduced. So to conclude, both three objectives were achieved: the actionable explanations, the existing knowledge, and also the out-of-distribution generalization. And the derived symbolic policies facilitate the assessment of feature importance inherently through analytical expressions. And what do I mean by that? Is that instead of having a post hoc tool saying whether the temperature or the wind speed is most important, you can directly receive this information from the policy itself, whether a feature or a variable is included in the policy or not. Also, it performs as actionable explanation thanks to the rule-based form of the enhanced grammatical space. So if you have those simple rules that if you are above or below the mean imbalance price, for example, this is also something that we can work on and make our decisions, our informed decisions based on. Although we must note that other applications in the energy sector, like overloading, include spatial dynamics, such as sequency, latency, or dependency chains, which have not been considered here. Thus, a challenge is to develop methods that impose a structure on the resulting output that reflects this physical topology, those causal leaks, or dynamic behavior. In this direction, we researched novel methods for interpretability in power grids. And why is that? Because the notion of topology is fundamental in power systems. Every node, bus, and line affect each other, and the changes propagate through the system. There is also high independency of variables, as voltage, current, frequency, etc. They are tightly coupled. Also, those systems have physical constraints that we need to respect, like stability margins, generation, and load limits, and the phenomena are most of the times correlated. So voltage collapse or cascading failures are not isolated, and they occur in chain. All of those aspects, they cannot be captured by simple symbolic, let's say, policies. Thus, the objective now is to propose a method that imposes a structure on the resulting output that reflects all the above aspects. And here is where we started looking at fuzzy cognitive maps. Why? Because they are graph models. So already we are, let's say, somehow it's easier to depict the topology of a power grid. Those graphs include n nodes or concepts, which denote the system components. and their weighted ages describe the causal interactions between the concepts. So the magnitude again is representing the strength and the kind of causality between them. Each concept has an activation value, and at each iteration of the reasoning process, it reflects its current activation level. And on top of that, Lee and Kinman information flow analysis, which is a robust framework that reliably assesses the causality in multivariate time series data. It is capable of identifying causal relationships in both linear and nonlinear systems, even under extreme measurement noise, which somehow builds the ground for something that's suitable for systems like power system, which can be highly noisy. So the combination of information flow with fuzzy cognitive maps starts with a two-phase learning process. The training phase one, we take the topology of the grid and then we translate it into the causal graph in order to reveal the causal relationships between the variables. Then we identify the statistically significant information flow rates, which then we introduce into the training phase two, which fine-tunes the model weight and parameters of the activation function and reasoning rule to fit the observed data. Our case study was an overloading detection problem. So we created a binary target. So one depicts the overloaded line 0 and the line in the normal operation. And we defined two binary classification datasets. The one for the line data and the second one for the different elements for the low and medium voltage as well as wind and generation. And why we did that is that we wanted to have a deeper granularity level on what are the elements that affect, let's say, the target line, which is supposed to be overloaded, in this case, the overload line 24, as you can see there. This grid topology that's highlighting the top 5, let's say, power loads and lines that contribute to the overload, it's inherently interpretable by nature. So someone that sees this picture can clearly identify that, okay, we are in heavy red, this is the most important, the MV load 0, the line 160, those are the key, let's say, reasons or the key factors that contributed to overloading in line 24. And this can be seamlessly fed into SCADA system, and it can create, let's say, ring automated alarms to provide some actionable insight on operation and operator dashboards. So how do we compare the output of such a method? We have done two things. First, an empirical study that we compared the output of the IFFCM with an explainable boosting machine and a logistic regression based on the frequency of each line's transition from underloaded to overloaded conditions during the overloading events. And then the model explanatory power was assessed by comparing the overlap between the lines identifying in this empirical analysis and the average feature importance ranking generated by each of the three models above. And then the second approach was a little bit more based on statistics. We selected three model independent feature selection methods like the MRMR, the univariate ROC-AUC, and the SVD-based feature rankings. And we selected those three because they also tackle different, let's say, parts of the interactions within the data. And just to understand in simple terms what we are comparing is that we compare the common feature count here on the left-hand side, the number of how many common features we have in the model of IFFCM, EBM, and logistic regression with the number of the top features that each one of those methods also ranked. So the key takeaway is that unlike the other models, the IFFCM combined high predictive accuracy also with some causal reasoning. And in order to conclude this presentation and give the floor to some future directions, the key contribution of this thesis is first of all, a step-by-step methodology for interpretability that provides a clear distinction between post-hoc explainability methods and inherently interpretable methods. The development of a symbolic AI algorithm, the symbolic learning, which is tailored for renewable power plant assets which aim was to bridge the gap between AI accuracy and human expertise, and also that allowed the experts to integrate their knowledge to facilitate trust in their decision. The application of the CN2 rule-based algorithm to uncover reasons behind power grid adequacy issues, and the introduction of a two-layer architecture based on information flow fuzzy cognitive maps for detecting and diagnosing grid overloads, which provides feature attribution and leverages built-in causal reasoning. Finally, the analysis of the impact of AI regulations on the energy sector, particularly focusing on the European AI Act. And overall, this research aims to bridge the gap between the theoretical research and practical application in a high-stake industry like the energy sector, providing robust tools and methodology that enhance decision-making process and regulatory compliance in an increasingly digital and data-driven world. Some areas for future work, depending on the different methods developed during this thesis, are for symbolic learning and expansion into real-time operational deployment. Given this evolutionary nature of symbolic learning, online learning seems that it would be really suitable for that. We can enhance the application by inclusion of battery storage, so adding an additional level of complexity in the objective function that we are looking to solve. The inclusion of advanced trading strategies in the grammatical space, so reach directly traders that perform in complex strategies and try to integrate those complex strategies into the grammatical space. For the grid analysis, we can optimize the performance in order to enable sub-minute predictions suitable for real-time operations for the information flow fuzzy cognitive maps. We can include some elements such as generator maintenance or outages during stress to delve into even a more granular level of detail, and we can evaluate the performance under varying noise conditions. And in general, some broader directions are that we can explore human-centered interpretability design. So in the end, there is a lack of evaluation of actual humans evaluating whether something is or it's not interpretable. Some cross-sector applications, like applying the trading method into other markets like financial trading, etc., which are different than the energy sector, and to benchmark with the new studies, because as you know, this is a field that it's booming. AI literature is all the time spreading again and again, so we need to be sure that we benchmark and we always take into account what is the newest development in order to benchmark our methodologies with. Some of the publications during this thesis are summarized here, and I've tried to cluster them into regulation-related, grid-related, and trading-related with the following color code. And I would like to really thank the Marie Curie Co-Fund AI for the Sciences, which sponsored, let's say, this thesis, the H2 2020 Smart4S, Erasmus Plus, and Min Paris International Mobility Program that helped me for a stay in Porto at the premise of Inesc Tech. And I would like to conclude with this quote from Marie Curie, that nothing in life is to be feared, it's only to be understood, and to thank everyone for your time.
Thank you. Thank you very much, Konstantinos, for this nice presentation, which I found very complementary in front of your manuscript. So we will move to the question and answer session, and we will start with your first rapporteur, which was Professor Vaccaro. So Alfredo, the floor is yours for your questions.
Thank you very much. Congratulations for your interesting presentation that, in my own opinion, address a very interesting and timely topic. Some questions. First of all, considering the application described in chapter 3, the optimal bidding strategy, I'd like to ask you, how do you manage the uncertainty of the data uncertainty? And second question is more specific. How can you update the learning rule of deriving by this process? And how can you describe the risk, the attitude, the risk of the analyst, of the decision? So, by summarizing, how do you model the uncertainty? How do you guarantee the robustness of the solution, of the strategy? How can you update the learning rule? How can you model the risk attitude of the analyst? It means if it is model risk moderately, risk high risk, and so on. That's my first questions of these on this chapter.
I would like to thank you very much for your detailed questions. Allow me to jump to the slides for this chapter, and I think this and slide 27 and slide 28 might support me in answering those questions. So, starting with the uncertainty of the data. That is a paramount concern that we had, especially due to the let's say, that accurate forecast of imbalance prices. So, that was something that we came later on in our studies. Why? Because in a practical point of view, if you think about it, we underperformed the point forecast. So you can see that if we just use the basic grammatic space, we don't have something that's meaningful. We have something that it's even, let's say, creating issues to that. So in this direction, in order to help us manage this uncertainty, we introduce those threshold functions. So the threshold functions allow us for having a specific, let's say, allow us for a specific margin for specific areas of either it's above the mean or if it's below the mean, and also above the 25th and 75th percentile. So by adding this into the grammatic space, we tried somehow to manage this issue or to overcome this issue. On the question about how to update the rules, as you can see from this slide, the human expert can, in each one of those generations, can intervene either in the reproduction or in the replace of the population. So let's say that you want to alter or to update a rule that is due to an unforeseen event. That, let's take an example, that there is a huge outage, you know about it from the news, it's not yet depicted in the data, you know that it's going to happen, a big maintenance. So in advance you can go and replace the population with some let's say analytical expressions that could consider that, and then continue, let's say, continue the learning of the algorithm based on the altered, already, let's say, human injected analytical policy. Regarding the risk appetite, you are right, this is a very interesting topic. But in this study, we didn't capture the different risk appetites of traders, but it would definitely strengthen the findings of a future research.
So thank you for your answer. So you don't consider the concept of online training, so a training which is continuously. It is a continuous process. Do you expect that the expert update the knowledge base and then the learning rule, if I understood well?
It's a combination. So online learning, when we are speaking about, let's say, real world implementation, that means that you have the model running all during all the operation time, you don't have the output of the best individual here because you never stop the maximum number of generation reached. And most likely you converge into a specific analytical policy, which in each generation will regenerate itself. If this one is the optimal and if the model has converged, then this will be the case. Then if you have the injection of the trader and then you alter the dynamics, you can either, now I'm just trying to formulate in my mind, but what you can either have a solution that it's better, or the injection of the trader might be somehow rejected by the model itself because it will underperform the existing one, which is the best performing in general, and it's not overfitting, let's say, this specific purpose.
I see. Another question. How does the expert, the external expert, could influence the performance of your method? There is some kind of dependency of the human expertise in the overall learning process.
Correct, because it's again what I previously said. If the human expert injects something, a strategy that is not performing well, then of course the algorithm itself, it will reject it. If there is a more advanced strategy that practitioners believe that it's going to overperform the existing, let's say, optimal policy derived by the symbolic learning, then perhaps it might influence it into a positive outcome. And a really illustrative toy example of that is the results that we had with the enhanced grammatical space. So instead of having just the simple operations, let's say we try to affect the performance of the model by adding this if then else function.
Okay, and I'd like to ask you some questions about the other application that you considered, the overloading prediction and the scarcity prediction. I think that, for example, for the scarcity prediction, one of the problems that you outlined is the fact that the knowledge base is not balanced because you have got rare events. So, for example, in the scarcity is fortunately is a very scarce event. So my question is, how can you deal with a database, a data set which is not balanced? Do you consider some kind of one injection method or to generate virtual examples or something like that? I'm not sure if I make myself clear.
Yes, it's really clear the question, but for this specific case study, the scarcity events analysis, it's important to note that we focused only on the expected energy not served binary target. So that means that among all the data set that was the output of the NSOA model for adequacy studies, we had a subset that was positive for the expected energy not served. Then we took only this data set. So we are focusing only on instances that the expected energy not served, and we treated it as a separate data set. So this one, yes, might be noisy, might be biased, might be limited, but just to be completely transparent with you, we focused only on these data cases, and we didn't inject any other. We didn't create any, let's say, true-like, or we didn't generate any fake and real-like looking data points.
But this paradigm could also be applied for solving classification problems, 0-1, for example.
Sorry, can you just repeat the question?
These methods can be applied to solve classification problems when the output is 0-1 Q1. is a discrete variable of output.
Yes, I agree, and we did so in the IFFCM with a SMOT algorithm, but for the CN2 algorithm, we didn't took at all the zero output, let's say, of the data set. We focused only on the positive expected energy not served. So we treated only this.
Okay,
Yes.
I see. Another important questions. Are you considering the same topology in your data set, or can you manage different topologies, changing topologies?
This is very, very interesting, but we didn't test any different topologies for the FCM. Although we highlight this as potential future research, I haven't included in the presentation, but I have included into the manuscript that we should check how by changing some of the concepts, thus changing, in fact, changing the causal graph. Because if we change the topology, then we need to change the causal graph, which is the training phase one. So we need to retrain the model or find a clever way to not need to retrain from scratch every time and receive, let's say, the convergence activation functions that we have already, and then try to inject that into the next one. Although I'm not sure if this will work, given that if we change the topology, new causal, let's say, significant information flow rates will arise, which might be completely different from the previous one, depending all the time on what item you're going to change in the topology.
Okay, and another issue, did you make a scalability analysis to check if these methods can be applied to solving large-scale problems? You have got a large number of input and output variables, large-scale power system, for example.
Here I have to admit that we need to perform a substantial effort in optimizing the IFFCM algorithm, given that the computational effort is really big right now. So if we increase the number of inputs, we will exponentially increase the time, which is not good, and I have to admit that. So in the current phase of IFFCMs, they will not perform well, or they will take a long time, let's say, to produce something that by the time that the output is ready, then you might have a different situation. So you might not be able to use it or to extract any meaningful, impactful information. Okay. This is the feature. Excuse me. Please go on. It's this one, the sub-minute, to enable sub-minute predictions. So for the moment, we don't have that.
Okay. But just for my curiosity, in which software have you developed? Did you develop your tools?
So symbolic learning, purely Python code. The IFFCM was a combination of MATLAB and Python script. And yes, CN2, it was in R.
Okay. Just a final question. As you know, probably in the introduction, you mentioned that transmission system operators are not very open to integrate artificial intelligence-based methods in their tools, as you analyzed in the introduction. Do you think that these methods that you proposed can help the large-scale pervasion of artificial intelligence in real power system operation tool?
Here I believe it's the most interesting point of this thesis is that operators trust what they observe, what they can observe. So presenting them with a black box AI tool that they can't really observe and understand the internal mechanics is of paramount reasons to not trust it. If there is an approach, if there is a way to facilitate trust to transmission system operators, to any end user in the energy system, I believe. So if you manage to facilitate this trust, I think you can lower the barrier a lot for accepting such innovative methods.
Okay, thank you. No more questions from my side.
Thank you very much.
Thank you, Alfredo. Then we will move to the second rapporteur. So, Spiros, if you hear us, the floor is yours.
Great. Thank you very much, Francois. Konstantinos, thank you very much for this nice presentation and the thesis, which I actually enjoyed reading. I just want to say I can hear my voice, and I think probably everybody that is online hears the voice when they're speaking. So I don't know if it makes sense that you mute while somebody speaks.
I have already muted the microphones for the jury here, but
yes,
let me know if this works now.
Yes, that works very well.
Now it's solved. Yes.
Yeah, that's great. Thanks a lot, Konstantinos. Okay, so it was a pleasure actually reading your thesis, and I completely agree that we need more interpretable AI tools. So your thesis is actually very timely and well positioned for the hopefully removing some of the barriers to have more AI tools in the energy sector. This is called the PhD defense. So our role here is, so from the other side is to probably attack if you should defend, right? So I will start with my first comment. So as I said, I agree with the motivation of interpretability. I want to challenge a bit the use cases that you have used to demonstrate your methods. And I think Alfredo raised a number of points that I have also noted. And let me go to the first one. So you found that we need to add this kind of expert knowledge or the human expert knowledge of the if then else rules in your symbolic learning application or method that you introduced in order to outperform other methods like the analytical queue. So my question is, couldn't we also integrate the if then else rules in the analytical queue method? And now you are muted or I cannot hear you. Yeah.
Now? Yes.
Yes. Excellent.
Okay. Thank you for the question. So just to summarize again, if we can use the if then else into the analytical quantile. So I will go to the slide of the analytical quantile, the problem formulation. So the analytical quantile is the mathematical optimal, let's say, method if the imbalance prices were known in advance in order to minimize this imbalance cost. So from this perspective, altering this equation will result in something that is suboptimal. If we are speaking about the predicted imbalance penalty prices, which is the case now, we wanted, and we also, that was part of the first approaches that we tried to see how we can further, let's say, fine-tune the analytical quantile with some additional if then else rules. Why I didn't showcase this either into the manuscript or to the presentation today was that the results were quite complex. And what I mean by quite complex is that in the expressions, instead of having that if you have the price that's above the mean, then you do that, you had a more complicated structure going back to the inverse cumulative distribution function that then you needed to check, let's say, the different power quantiles, and the expression bloated. So if we are looking for something that a human trader could directly see and make the decision, that was not the solution that we were looking for. In terms of accuracy, indeed, it performed better or equally well with the typical analytical quantile when we had those, let's say, interventions, and when we injected, let's say, this into the training of the model, but we somehow deviated from the objective of the thesis, because we ended up with something that, yes, it's analytical, but it's not that simple. And we tried then to tune a lot of penalty metrics in order to achieve, let's say, something that it's analytical, simple, in, includes only 2-3 variables, but I wasn't able to achieve such a solution.
Okay, that's very interesting. But then how long did it take you to train that model? Because, and how long does it take, for example, to compute the analytical, let's say, benchmark, if you want, compared to the training that you performed? Again, you might be muted, or I cannot hear you.
Now? Yes.
Yes.
There is a slight delay between opening and connecting, so apologize for that.
Okay, that's good to know for me as well. Yeah.
Can you please repeat, because I...
Yes, of course. So I'm wondering how long it. I don't think I found that in the thesis. How long did it take you to train?
Yes. Yes.
Your symbolic learning compared to, I don't know, the analytical, which might be,
yes.
faster.
Yes. So we need to make the differentiation here between training in order to receive that kind of expression and using this expression. Because analytical quantile, it's fast because we're just using that. Here, it's also really fast if we just use, the wind speed that we currently have. We just implement in this function, and in a split of a second, you have the result that you're looking for. So it's a different thing on how we end up with that, and how this will be, how long will this take in order to produce, let's say, the megawatts that you're going to bid. For the training of the model, in order to achieve and to reach, let's say, those policies, approximately for the, let's say, 2017-2022, it was historical data for, let's say, approximately 5-6 years. The Python code took me around 20 minutes in order to reach 50 generations, so 50 iterations of this round. But those 50 generations included also the different clustering. So 50 generations of each one of those different approaches that I highlight here. So global, hourly, price spread. So I guess if we divide it by 3, it's under 10 minutes, the computation time that it
really
took.
Okay, so this with this 128 gigabyte of RAM desktop computer you had, and the Ryzen.
Yes, this one is the detail for the desktop use for the IFFCM, yes, which, to be honest...
Is it the same that you used?
No, it was in a later stage.
Okay.
I don't recall exactly the specs of the laptop that I ran that, but yes, it was in a 9-core Intel laptop, which I don't recall the specs on the gigabytes, on the RAM.
But that's actually faster than I thought. If it's only 20 minutes, or
in the beginning, so just to be clear on that, in the beginning, when I haven't optimized the code, etc., I started with approximately 1.5 hours, and then starting to find bugs in the code and reduce, let's say, the errors in this heuristic process. So it wasn't from a solution that happened just in... it took me 6 months, let's say, to reach these levels.
Yeah, I can completely understand that. So then, just a suggestion that I might have is maybe it would be interesting to see if you do this kind of analytical queue with the if-then-else rules, and you compare it to your optimal strategies that you find through your symbolic learning, and try maybe to extract an equivalent Because then maybe you might have an analytical expression or kind of analytical equivalence that one can explain the other, more or less. So if the analytical query is too complex to understand, maybe then the symbolic learning can help you interpret that better. Or just a suggestion, yeah.
A really interesting approach, yes.
Yeah. Now I want to go to slide 29. And I have two questions here, actually. Because you optimize both for the solar and the wind at the same time, right?
No, this might be a misunderstanding and misinterpretation. It's on my side that I put both in the same. It's two separate case studies.
Okay, good.
One for solar, one for wind, just to illustrate the different technologies and how we respond to different data.
Because also in the maybe I also missed that in the manuscript. I thought it was the same. But good, yes, because then my question then would have been that very different the sizes of the two. So the solar might be lost if it was training for both, let's say.
We started with the approach of a virtual power plant, and then we tried, let's say, to normalize the output of the two. But then we were lost somehow in the interpretability and translation between the normalized values. So we prefer to split and use the nominal values in the end.
Very good. And then I have another question that has to do with the split of training and validation set. And I would like to discuss this a bit because we're talking about time series. So then the sequence of the data plays a role. And then it's clear that the test set should be at the end because actually you need to train on historical data and then you predict the future. So that's great. But why does the validation are in regular intervals?
So as time series for solar and wind productions are really seasonal and depending on weather variables, having it only, let's say, for the first 6 months of the year training and validating in the rest 6 months of the year, and finally testing, let's say, in a full year, might cause some issues in terms of, okay, we have X amount of solar radiation during the winter, and then during the summer you have a completely different power forecasts. So this is the reason why we split it that into having, for the same months, we split it each month into half, and just to have a little bit better homogeneity across the training validation.
So how do you train then? Do you train each month separately?
No, we just we extract, let's say, the data for half of each month, and then we put them into only one time series. And there are the gaps there for the days that you don't have the data. So we just remove then those missing variables and we treat it as one continuous time series.
Okay. Sounds good. Then I have also one more question, or let's say similar. I would like to equally challenge, let's say, the approach with the causal, right? For the line overloading use case and the if FCM. So because you use that for line overloading, so you're trying actually to figure out for a line that is overloaded, what is the causal relationships. And for this kind of use case, wouldn't physics work best? Or do you get anything extra from what you trained?
That's a key question. And I have to admit that in general, the motivation was that, you know, we have to actually follow physics rule. We have to try to approximate what we already know. And this is really interesting, but the addition that we might have out of this is that we can identify some direct and indirect causal links. So, for example, the LV load 4 that you see on the top of this slide has an indirect, let's say, causal link with the overloaded line, which I'm not sure if we could capture, let's say, with the traditional methods. But yes, in general, we are trying to explore something new, and that was the main motivation, let's say, of doing so.
Okay. How do you explain what does indirect mean? So what would that? How can I understand that?
Yes, indirect might help to go to this even here. So I can present it, and you can show the pointer. Okay, so let's take the example of the element on the concept C2, which could be a line, could be an element, whatever. And this C2 is directly connected with the causal information from C3, C1, and C4. And it's indirectly connected with C5, as C5 is connected, let's say, with C1, which then is connected with C2. So this is the only difference, let's say, that we can observe, that let's say a line that it's not directly connected with this specific concept can affect, and how it affects the target line that you're looking at. I don't know if this is, let's say, a great example, but this is the essence behind the direct and the indirect causal link.
Okay. Yeah, so it would be interesting to see also what this means in this example. And also, okay, but that's good. Okay, so this might offer some more information. I will not go more into this. Yeah, then I see that I may have. I would like to ask one or two more questions, and that's related to the introduction. Because so at the even at the preface, then you have a statement that AI tools lack three fundamental traits: curiosity, doubt, and worry. And I want to challenge the curiosity. Why do you state that, or why do you claim that AI tools lack curiosity? Because I would claim that exploration of a reinforcement learning agent is curiosity.
Okay, so maybe we step a little bit off the ground of energy sector, and we go a little bit about a broader discussion on AI. Curiosity itself is not an intrinsic, let's say, property of a model, of any model. I'm not speaking about AI. I'm speaking about even any statistical model. They are math, and they are a combination of let's say, math expressions. So the human need to learn more, to understand more, to ask why questions is not intrinsically, let's say, included into that kind of even complex, let's say, math structures. Then it's the so-called discussion of the AGI, the artificial general intelligence, etc., which I believe that even with really big advancements and huge leaps that large language models have made, they remain purely mathematical models, which lack this, let's say, need that we as humans have to understand the world around us. The only reason that a model would try to ask those why questions is that if those are, let's say, asked or requested by its human operator, or by, let's say, the engineer that develops them.
Okay, interesting. Interesting because I think there maybe we have a different interpretation of curiosity. From what I understand now, you focus more on the why, and maybe an AI model does not ask why. I'm not sure, but maybe. While for me, curiosity would be the eagerness to explore. And I think that a lot of AI models, that's why it's called artificial intelligence as well, right, are exploring and trying to figure out the environment and what else they can do. But that's an interesting discussion. Very good. I'll stop here. Thank you very much for the discussion, Konstantinos. Back to you, Francois.
Thank you very much.
Thank you, Spiros. So now, Konstantinos, I will change my role. I will take the one of rapporteur. First of all, thank you for your report, your nice report. I must admit, I learned quite some new things, and I found it very, very cool, very interesting. And so I have questions. Some of them were already asked, so I will not repeat them, but somehow I have someone left. My first question will be about symbolic learning. So if I'm right, it allows the participation of experts in the learning process. But I was wondering how accessible is the tool for a power system expert? Should he be also an expert in AI to use your tool? So this would be my first question.
This is very interesting, and quite frankly, in the current development, it will not be easy to use it. But the code itself, if it's used in the user-friendly environment, I have seen that there are a lot of companies actually doing that for symbolic regression. So there are some easy to use user-friendly environments that you import the data, you import the output of the model that you want to approximate, and then they create the surrogate models. I believe that if such a user-friendly environment is replicated and the code is changed in order to request for the objective function from the user, then it will be as easy as a click and go.
Okay, thank you. Yes. With regard of your prospects, so you were mentioning that it would be interesting to include storage, a battery in the decision-making framework. Maybe one other option would be to include flexibility as a whole, and a lot of flexibility for now is located at the low voltage level. And in the end at the customer level. And so it's also important for him to be able to have some interpretability in the decision he has to take. And so you are speaking about experts, but in the end, should not everyone, so every customer, be able to access the tool? It's a philosophical question, but what do you think about that?
It depends on the need. It depends on whether we are looking at, let's say, the trading case. Yes, if someone that's not familiar with the structure of the markets, etc., access this tool, and it, let's say, includes some naive inputs that they have nothing to do with the market, most likely it will create something that is performing worst.
Yeah.
So you need to have context-dependent experts. Let's define it like that.
Okay.
And regarding flexibility, allow me to comment here that my supervisor Ricardo would be really interested into studying this even more in the future, I guess, because there are a lot of studies on flexibility, and the merge of those two works might be really interesting.
Okay, thank you. Another question. So you maybe know, but for the moment, another very interesting trend in machine learning applied to power system is decision-focused learning. And in the end, would I be right if I say that your symbolic learning approach is somehow decision-focused learning with interpretability capabilities? Would I be right in saying that?
I have to admit that I'm not quite familiar with the decision focus learning definition that you mentioned. So I would prefer to not comment on something that I'm not that
okay, but
familiar with.
when you apply decision focused learning, somehow in the training phase, you bring some information about the optimization problem you have to solve to the predictor. And I had the impression that somehow the underlying optimization problem was also fed to your symbolic learning, but yeah.
No, it seems like this is the case. If this is the definition, it seems like this is the case because we have a specific objective function, the specific decision that we focus on, and this is what's happening. So yes.
Yeah. And so in that direction, is symbolic learning applicable whatever the underlying nature of the decision-making problem you have to solve? So for example, here it was about the imbalance problem, but if you change the problem by a nonlinear one or something like that, would it work?
Here it might be worth mentioning that the majority of symbolic algorithms and specifically symbolic regression is used in other fields, mainly in medical field or for protein structure exploration before the, let's say, the huge leap with DeepMind, etc. Most of the work that was on different protein exploration due to the structure of these tree-like policies, they represented chromosomes and stuff like that. So the majority of the literature was already in that. So I would say it's quite the contrary. The application into the energy sector is something like comes on top, which was not the normal case, let's say, for the majority of the literature, whereas most of the applications are outside the scope of trading.
Okay. Okay. Maybe a question regarding your application to the detection of overloaded lines and the explanation about that. And it goes in the same direction as the one that Alfredo asked earlier. I was wondering if you had to apply your EFFCM method to highly meshed transmission systems. What would be what would be the impact of a complexified topology on the performances of your system? Can you have some? I know you didn't test, but can you have some insights about that? Because the more you will apply it to transmission system, the more complex will be the topology of the system, of course.
Correct. The more complex the topology would be, the more complex the matrix of the different causal interaction would be. Thus, the more complex and the more time-consuming the decision would be in order to converge, let's say, to a specific area that we would be able to understand what are the main contributions. So it's complexity in terms of more nodes in the network is directly, let's say, following a complexity and increasing computational time here. So it will be difficult to do. Yes, after some time, after a while, you will have the solution, but I don't know what would be the impact of having such a solution. Maybe for a post hoc analysis of an event that happened and you want to analyze what were the key reasons, but for real-time operations, I think it will not be the case.
Okay. And in that direction, when you have a congestion, you can take some corrective actions which are about changing the topology of the grid using some breakers or things like that. And if you do that, I guess it will have some impact on your matrix. So do you need to retrain everything?
Yes, I think this is more or less the problem with the causal graph that I tried to describe, that due to the first training phase of this model being the translation of the actual grid topology into this causal graph, you will need to retrain everything.
Okay.
And we have to explore if there are potential ways to retain some of the already identified causal relationships between the parts of the grids that they were not altered. Although I'm not that confident to say that now, because most likely changing the topology will affect the full structure of the grid.
And if you retrain, how much time will it take?
So in this case, the time that took us to train the FCM for this MV Oberheim network was quite substantial. It took more than 2.5 hours to receive the results.
So
although the same, let's say, optimization and the same efforts that I performed for the symbolic learning, I have to admit that they were not performed in the same direction. You have bridges between MATLAB code and Python code.
Yeah.
Of course, there are a lot of areas of improvement here.
Yeah, okay. Because if you want to apply that to close to real time, it should be fast, I guess.
Yes, yes, but it's once again part of this sub-minute aim, the objective of achieving this in sub-minute prediction.
Okay, thank you. Yeah, maybe, but it's maybe not a relevant question. It's a curiosity question. But yes, in your adequacy study, so you made the sampling, or you had the samples, and then you try to identify let's say the scarcity conditions and situations. But I was wondering if we could use your approach to do the reverse way, and to try to orientate the sampling, and to maybe not sample 8,760 hours, but to directly, let's say, improve the exploration of the uncertainty space to reduce the number of samples you have to treat. Would it work, or is it totally non-relevant what I am saying?
No, I have to admit that's an interesting approach. Although we have to be really careful to not exclude, let's say, specific instances that were not correctly explored due to the limited amount of data compared to the full-time series used in this adequacy study. I think this is a major constraint that we have to keep in mind.
Okay. And maybe a very last question. So, and I'm coming back to symbolic learning. So you have an initialization phases in your symbolic learning process. And I was wondering how important was this initialization phases, notably in terms of convergence, and in the end, does it always converge whatever the initialization you use?
Yes, it's again, I have to be careful with the answer. Yes, in general it converged, but it converged because we used the same grammatical space. If we initialize our population with a constricted, let's say, grammatical space of potential solution that can explore, potentially it would converge to something that it's not that optimal. For example, if we just have addition as the only operator in this space, all the solutions would be in a format of something like this, without, or let's say, losing the advantage of having different types of interactions between the variables. So in this case, it will not benefit our purpose. But in general, due to this random sampling, sorry, it's here. Due to this random selection, and then within this random selection, we select the best performing individuals. the algorithm tends to not overfit. It tends to generalize quite well.
Okay.
So I believe that it would converge, although yes, it's always important to generate this initial population, even if not randomly, with solutions like the one Spiro suggested of having the analytical quantile. But this again comes into the grammatic space. So the better the grammatical space is defined, the better the solutions would be, or the convergence would be achieved.
Okay. Thank you very much, Konstantinos. So I will change again my role. So I will now take the role of chairman, and I will just give the floor to Anna then. Thank you. But I don't know if Anna is speaking, but we don't hear the questions.
We are fixing it right now.
Okay, sorry, my apologies.
Yes, no.
Can you hear me now?
Yeah, now it works.
Perfect. So first, I would like to congratulate you for the wonderful presentation that you did today. That was very clear and pedagogical. And of course, I have some questions. And so first one concern symbolic learning part. And so you mentioned that you mentioned some training time. Was that for the basic grammatical space or for enhanced?
For the enhanced.
For the enhanced.
In my previous answer, yes, it was for the enhanced.
Okay, so then it's much faster than I thought. Then I have a maybe that's not relevant for the example you studied, but maybe you could still think about that. Is there any possibility to automatically detect that some grammatical space is not expressive enough for my problem, and maybe how would you do that? And so then a related question, can we instead of switching from the basic to enhanced grammar, is there a way of doing that adaptively, suggesting which operator we should add, and how would you think about that?
Thank you very much. It's a really interesting question, but I have to clearly understand whether the possible space of expressions is defined by us, or it can be automatically defined. So if there is a way, the question is that if there is a way to automatically find a better space of potential expressions in a broader way, or if we have, let's say, a given space of operations, and then we start with taking subparts of it. So we initially start, let's say, with taking only 2 operations, and then we see how we can expand this. Just
so let's imagine the first step that you do have a given enhanced model, but maybe it's so big that you don't want to include everything at the same time. So it could be seen also as suggesting an operator,
yes,
because you don't want to explore all possibilities that you have. But let's say that this actual space of possible enhancement is done.
Yes, this is really interesting, and the closest thing that we have performed to that is, I think, with the penalty metric changes, that we try to implement an automated way to either restrict or enlarge the penalty metric, that we somehow say that, okay, this is too big, you stop, and you have to search another field. So I think it's quite similar to that. We have done a lot of effort to try to automate that, either by doing grid search or Bayesian optimization, etc. Unfortunately, I wasn't able to derive a concrete result that I could include, let's say, into the manuscript or into this presentation. So I don't have the answer to what will be the most efficient way to do so. What is the issue and what was the main cause of not being able to have this problem is that in each iteration here, maybe I will put it like this, the random selection that we made alters the nature of its policy. So we cannot somehow control this random, let's say, change between the different policies, or I wasn't able to identify the correct way to do so. So this was a major, let's say, limitation in automating this. I believe yes, with some not big, but with some effort, it could be achieved to have an automated way in order to search. And even now, allow me to make a step even further. Even by somehow integrating more advanced exploration tools. What do I mean by that? That instead of having explicitly set rules, that there is a way that this learning could browse the internet. I don't know, and try to retrieve the state-of-the-art grammatical space that is available right now. That could be a very, very theoretical, let's say, example of, okay, there is a way to even expand the space of possible expression by searching outside the scope of what I already know, what let's say, the human expert provided me with, and try to also search alternatives that's available on other unconventional sources, let's say.
Okay, so but I guess that would require lots of computational power.
Yes.
But so maybe I'm going into the opposite direction. Then can you think about what would be the criterion to, let's say, like trigger the alarm? Okay, this current grammar is not enough. So how would you do that? So this is actually the first step in then trying to expand the
yes,
space.
So the alarm would be triggered whether we don't have a convergence. If we experience that we have a lot of iterations with big variance. In specific numbers, I cannot say exactly. No, after 3, after 4 generation, all this is really use case dependent.
Okay, but you would frame it as detecting variance.
This is one alarm that just comes into my mind now. I don't know. So,
because we could also have a situation that it converges, but to some subspace.
Yes.
And that is very far away from the actual formula you would like to obtain. So
in this case,
that's very tricky to adjust, because if you don't know
the ground truth. Okay. So yes.
Okay. So you mentioned at many points in your presentation robustness. So can you develop what kind of robustness do you have in mind? Is it to stochasticity, or maybe to some modeling errors? Or
yes, explicitly, I think I mentioned robustness here. Okay, never mind. What I wanted to highlight is that we need to test, let's say, those strategies under different noise levels. For example, how they would perform under such scenarios. And if you can help me identify exactly where I mentioned that, it would help me a lot to.
Oh, it was at the beginning, but also I didn't note the number of the page. So
okay.
It was also when you in the information flow FCM
yes.
setting, and I mainly in that setting actually.
Yes.
So.
Okay, that the information flow is a robust framework. Yes, this might be, let's say, a characteristic that I just wanted to highlight, that it's a mathematically robust framework. Where if we go into the details why in Lian-Kingman information flow is mathematically robust, allow me to, let's say, I have to go and study in more details the maths behind it. Why I'm saying that? Because I use this model due to the library that I found, and due to the characteristics that the paper highlighted, that it's robust in different measurement noise and in high, let's say, noisy environments. And this is let's say, a gap in my thesis, that I didn't went into details under the hood of the library to explore this mathematical robustness. But I just used it based on, let's say, the paper description. So okay. This is a.
And then I have questions. Actually, in the setting of detection of overloaded lines. So it's related to some other questions that were already asked, but just to better understand. So I see. So basically, you are going to detect that something is going wrong, and then trigger alarm.
Correct.
And so, as operator, I imagine I do have some sort of knowledge of the system and some current practice that they are doing. But then I would like to have some more suggestions. And so, is there anything that you could add to your? So typically, this is also the case in medicine now, that the AI tools
system.
are doing recommendations.
Yes.
So once you detect that there is an issue, does that allow you to suggest potential actions to take? And of course, that would leave the possibility to the operator to follow them or not, or to go with business as usual. So,
yes.
So they do not need to depend on AI if they don't want to. But this gives an idea. Oh, I forgot. This is actually a great thing to keep in mind, right?
Yes, so in this direction, the so-called recommendation system came through this importance rank. So we can say that it recommends that if you alter something into, let's say, the envelope 0, then potentially you could, let's say, avoid, or you could fix the issue that you have in the overloaded target line. Although I'm not that sure that the recommendation system that you are referring to could be summarized in a simple importance ranking table, or if you would prefer having some, let's say, easy to calculate table on rank rules. So each one of those lines have a specific metric, and giving this, let's say, ranking table of all the lines, then you can perform some analysis, or you can check whether this and this happens simultaneously, what is the risk score. So risk scores, it's another very interesting area for interpretable AI. I've seen some works on that. In the very beginning of this thesis, I tried to implement those risk scores, but yes, in the end, we didn't include those risk scores in the IFFCM approach.
Okay, and one question concerning perspectives that you mentioned. You mentioned online learning and the dynamics of the system, and that makes me particularly happy because I like reinforcement learning and that's in highly dynamical systems. And so, what would you see as interpretable AI in that setting would be something really valuable. But it's hard. So what do you see as a possible first step for some use case you can think of that would go a little bit further from what you currently have into the online setting?
I think the step towards the online learning setting, it's not that far-fetched in the terms that the output of the model would be exactly the same. So you can have a graph, you can have a graphical illustration of the bidding decision that it's altering according to the new information that you are receiving. So just to bridge back, let's say, and go back to the initial question of Professor Vaccaro, here this iterative process produce, let's say, the policies, and then we stop. It won't change a lot if we continue to produce those changes iteratively without having the stopping criterion. So the concept of online learning, I think it's just the difference in the implementation on how to incorporate the input data. We directly train it, and then we iteratively, let's say, receiving or gaining the most updated analytical policies. But in terms of implementation, I believe it's not that far-fetched goal or next step to make. It's just how you would streamline the input data and how would you present the output in a continuous environment.
So there might be maybe some issues of stability to address as well. So, but
yeah, I mean, if we go to online learning, it's not only stability; it's also the quality of the data. Because if we are receiving data which might affect or which are let's say biased or they are affected from some errors due to the API that we receive, for example, this data, this needs to be addressed. Otherwise, this would affect the quality of the output. So yes, thinking about it only from the symbolic learning algorithm, it's easy to do. In practice, it might be a headache.
Okay.
Yes.
Thank you.
Okay, thank you very much, Anna. Then we can move to Panagiotis.
Yes, thanks.
The floor is yours.
Thank you. So, okay, congratulations from me also, Konstantinos, for the presentation, for the thesis, and for your work, of course. I think a lot of my questions have been covered so far, but I'll try to maybe go back to some of the concepts, even if we discussed, just to put some specific thoughts or specific directions there. I'll take you first a little bit to the bit where you talked about the grammatical space. So can you go to the slide where this one? Yes, 23, yes, perfect, thanks. So I wanted to maybe touch a little bit back again on the complexity of the grammatical space and how do you define it, or how do you define how happy you are with the complexity that you have chosen? So can you comment a little bit?
Yes. So the complexity in general is not just for the grammatical space. We have defined this again. This is, let's say, part of the research that was not even in the manuscript. That the penalty metrics that we searched were basically the number of the operators. So how many different operators you might have. This is number one of the complexity. Then we had a complexity combining the input features and the number of the operators, which in the end was the best and the best approach in terms of reducing the expression derived, for example, here. So we try to balance between how many operators we're going to have and how many different variables we're going to have in the analytical expression. What do I mean by different? Here, for example, when we have wind speed squared, actually we have the same variable 2 times with one operation. So you have the multiplication of wind speed. It's more easy, let's say, it's less complex rather than having wind speed times temperature or something like that. So that was another way to quantify this complexity.
Yeah, thanks for that. So when you were deciding how to augment, let's say, that space, so how did you make the choice? For example, you chose 25 and 75 quantiles, so why not 20 or 70 or 65? Or...
Yes. This is also very interesting. We choose, it's here in the grammatic space, here, the 25th and the 75th percentile. We try to use as basic if then else methods as possible. And okay, what is the easiest way to do that? We divide in the center, in the 25th and above, and the 75th. So there is not a complex or a, let's say, very, how to say, very formal way that we made this decision.
And can I ask you how does this process, if you will, link to computational complexity? Like in a real setting, would someone potentially need to try this a few times to get it right? Like, for example, to get the grammar correct, would you have to iterate a few times and maybe try this function or that function based on human expert knowledge, for that matter? And how does that link to computational complexity? You know, if I chose to add 10, for example, here functions, would that blow up, explode the computations, or could I try that? Or
yes, this again is very interesting. Why? Because the addition of grammatical space will, of course, have the correlating effect into the space of the possible expression. So if the space of possible expression explodes, even with the solution that I previously said, that browsing the internet and stuff like that, computationally it will be let's say a dead end in after a certain number of expressions. So yes, the more expressions that we include, the more the complexity of the model and the more time it takes to.
Do you know formally if there's a link? Is it like exponential or linear increase? Or
no, I haven't done exactly the formal link on.
Okay, it's very good. Thanks for that. So right. Maybe also I would like to ask you a bit about the now the IF-FCM method and the definition of the 2 layers as you presented it. So yeah, that's a good example here maybe. So can I ask first, if you go, I think it's on your previous slide, if I'm not wrong, where you how do you define the causal graph effectively? So is it just purely based on the graph of the power system? I think your
this one.
Yeah, this
one. Yes.
Yeah.
So the graph of the system, it's not purely, let's say, depicted into the causal graph, but the information of each one of the nodes I mean in the causal graph now, it's each one of the elements. So this is why I need 2 layer approach. Why? Because a node in the first layer is a line. So it's a little bit complicated in the power system sector, because those C are the concepts, let's say. Each concept is a node. So in the first layer, that's the reason why we had 2 layers, because somehow we had to depict those lines as nodes in the IF-FCM. And this is why we weren't able to include both the nodes, I mean, both the lines and the elements connected to them. Thus, in order to have the granularity needed, we performed two FFCMs, one for the lines, one for the elements to receive the granularity needed.
And when going through this, I wanted basically, Emil, a little bit more open-ended question. So what was the motivation behind choosing these two approaches? So, and maybe with respect to a practical application as well. So how would someone act on the information from the lines, from the overloading of the lines? And how would someone act from the second layer of, which has units and loads, as I understand it?
So from the design from a practical point of view was first to detect the lines, and then if you want to have a better understanding or to have if you want to search on why this specific line, you have to go and check what are the elements connected to this line. That was the initial thought even before starting all the modeling process for that. And in the end, it appeared to be correct, this concept. Why? Because here the load, let's say the MV load 0, indeed was the one that was closer, let's say, to the overloaded line. So it may have some, let's say, physical understanding, physical reasoning. I don't know how to properly express it on just by viewing the importance rank, understanding both layers in one way, instead of having like a features ranking of, okay, it's MV load 0, it's MV load 1, and then try to assign and to allocate where this is connected to which line and to which node. Having this graphical structure somehow helps us intuitively understand the key factors, the key lines behind.
Based on the causal, let's say the strength of the causal link.
Yes.
And I think this is a good link to my follow-up as well here. So have you tried then validating this with a physics-based approach?
So
like a model, AC power flow model or something?
Yes, like unfortunately not. Although this would have been the best approach to have this, let's say, ground truth evaluation with the other models.
Yeah.
Instead of just looking at the empirically the transitions between the lines, doing this would have helped a lot. Just allow me here to mention that this work was done in the last phase, in the end phase of the PhD, and
there's always something more to do. Yeah?
There is always something more, and in this case, it was really important. I have to admit that this comparison is a really important comparison that needs to be made.
Yeah. And maybe one last question, if you can go back to the slide where you did the feature importance for the, I think it was the previous one. Yeah, there you go. So the next one, sorry. This, here, that's the one, so 45. So this one here, so again, the validation, let's say, of this, was it just based on what you presented here? So between the methods, to put it that way, between these three methods, logistic regression,
EBM, explainable boosting machine, and FFCM,
and your proposed method. So was it this the validation of? Because again, my question would be, what's the ground truth? What's the really most important feature there?
Yes. So in order to answer this question of what is the ground truth without doing the tough work, let's say, we proposed having a common understanding. So we have three feature selection methods. Those three were different from each other. I mean, they were model independent, so we weren't biased towards EBM or FFCM. And we use this as I said, the area under the curve as the indicator of how many common features each of the models that I have already, let's say, calculated for this specific grid are in common with the feature selection methods here. And we did this for both layers, and it's marginally, I have to admit, for the other two, the difference is marginally, but there is a trend to that the FFCM was a little bit overperforming in this direction.
Great, thanks a lot. congratulations again. Thank you.
Thank you.
So,
Thanks a lot, Panagiotis. So now we will move to the supervisors. So maybe we can start with Simon. I don't know if you have questions or something to say, Simon.
Yes, can you hear me? Yes.
Yes, yes.
Yes, super. So Konstantinos, congratulations. Thank you for collaboration. You managed to cover a quite wide spectrum of both models and application. So I think you got grilled with many scientific questions. I have one question. It's not scientific, really. Now that you are starting a new life in the private sector, which you already knew before the PhD, but you go back to private sector. How do you think you can be inspired by this interpretable AI? Will you use that even in management tasks, or how would this be useful for your professional life?
Maybe may I be completely crystal clear with you? I use it a lot, and what do I mean by that? Is that maybe for everyone to be on the same page, I work in the private sector now for a family office. So the owner of the company is of a certain age, and he has to take very, very complex decisions with high risk and quite some substantial financial implications. So the more easy and more interpretable I make those complex decisions to him, the better my feedback, let's say, or my KPI metrics are. So, the overall objective of simplifying something and the overall goal of less is more directly applies to a lot of aspects in this career life.
Thank you. That's all for me.
Thanks a lot, Simon. Then we can move to Ricardo.
Okay, so I also congrats to Konstantinos for all the work. I have actually a scientific question, but more a generic one, which is, so nowadays we heard a lot about explainability and even using Gen AI for explainability. So how you see, because when you started the thesis, there was not this wave of generative AI and large language models. So after all this, more than 3 years, how you see your work within this new context on AI in terms of generative AI and large language models?
Thank you, Ricardo, for this question, because it's a thing that really impacted the journey of a PhD candidate. In 2021, no one knew about AI. We discussed with Panagiotis in a scientific conference about explainability and interpretability in ISGT, and we were a bunch of electrical engineers. Suddenly, after, let's say, a boom of the large language model, specifically GPT-3, everyone was interested in the topic. Why? Because I think that in general, we want to somehow do again less tasks instead of doing more complex tasks. So having a large language model doing the work for you somehow sparked the interest for a lot of people in the, so a lot of news. It became a trend. Then a lot of individuals capitalize on that. A lot of revenue was generated. And all this really affects a PhD student when it's trying to research something and suddenly he competes with companies, bringing millions to the market, selecting the best programmers, the best individuals. So you're coming from from a really good and reputable research center, but with let's say your laptop and your coding skills, and you have to compete with huge organizations. I've heard that a lot of PhD students that they were working on this AI were exhausted. They just couldn't, complete their thesis. They couldn't complete their work because they felt all this pressure. And I have to admit that I passed through a similar phase. In the end, we see that you have to do your best. We have to keep pushing research, and instead of just listening to heuristic parrots, as they say, the LLMs, to look at the fundamentals, to try to understand why we should trust or we should not trust those models, and how we can use it in order to accelerate the true research and to accelerate the true critical thinking. So thank you very much for giving me the floor for speaking about this, Ricardo. Really appreciate it.
Okay, thank you. That's all from my side.
Thank you, Ricardo. And then, last but not least, George.
Now, yes.
Now?
Yes.
Okay. So I would like from my turn to thank you, Konstantinos, for the hard work all these years. This last period was challenging because you had to cover to do the work to prepare for defense and all the professional obligations, but I think today we are happy from this feedback we have with the presentation. I don't have any question. I think we have discussed a lot in the previous days, months, etc. I would just like to thank Ricardo for the collaboration in this supervision of this test, and Simone and the jury for participation, for evaluating this work. Thank you.
Thank you, George. No, I don't see the room, but if there are some colleagues in the room that want to ask a question about what Konstantinos just introduced to us and nicely defended, the floor is to the room, the public.
Okay. There is a condition to have a PhD. There is one person here who has, but she does not have questions. So
okay, so then I guess we can close the Q&A session at this stage, and the jury will deliberate then and come back in some minutes. So yeah, we are coming back.
Thank you very much.
Hello again, Konstantinos. Do you hear me?
I can hear you, but I don't think they are hearing us. If there is someone in the room.
Yeah, I don't know if there is someone in the room.
I think there's no one there.
For the drink.
Yeah, I don't think there probably is no one there.
Okay. Do you hear me in the room there in Nice? Yes?
Excuse me. Okay, Spiros is there. Okay.
Can you hear us?
Yes. I think everyone is there. So Konstantinos, I will start with the result of our deliberation. So today, on the 16th of May, Mr. Konstantinos Parginos defended his thesis entitled "Advanced Methods for Enhancing the Interpretability of AI Tools in the Energy Sector." He gave a very clear and confident presentation of his research work. The candidate, using excellent support, covered the motivation of the work, the main results, and promising future direction of his work. The candidate was able to condense and communicate the work done during his PhD study, covering all the topics he addressed in the thesis, thus showing his pedagogical skills. The jury asked questions covering a wide range of the topics from the thesis. The jury focused on the motivation behind the choices the candidate made for the problems he posed and the solution he proposed, and how the solution he proposed compared to the current state of the art. The candidate answered in details and in a very satisfactory manner the many questions asked by the members of the jury on the promising subject of interpretability in typical energy applications. He showed his excellent knowledge of the tools developed, with a lot of insight, highlighting limitations and alternatives, and opening up numerous perspectives for future research. The jury appreciated the impact of the work in both academia and industry. For all these reasons, the jury unanimously decided to award Mr. Konstantinos PARGINOS the grade of Doctor in Energy and Processes of Paris Science and Earth University, prepared at Mines Paris PSL, in the frame of the doctoral school number 621, Ingénierie des systèmes matériaux mécaniques énergétiques. In addition, the prerequisites for applying the European doctorate label have been met. So congratulations, Konstantinos. And now the floor is yours for the oath, I guess.
First of all, I would like to thank you very much, the jury. Should I first say the oath and then the thanks? Okay. So, in the presence of my peers, with the completion of my doctorate in energy and processes, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, to my methods, and to my results. Thank you very, very much.
Thank you very much. So I think that my job is done, but I guess that maybe there will be speeches, or I don't know. So I let the floor to you there, Ines.
Perfectly done.
Thank you.
Okay, so before leaving, allow me to thank one by one the jury member and the president. And I can understand that you have a very, very busy schedule. So if there is a need to drop off this conversation, please feel free to do. I don't want to, make it even more complex for you. It's already 2-3 hours that you have contributed with your comments that I really, really appreciated. You have given me future directions that we can further enhance this study. So it's really, really appreciated, and I would like to thank each one of the jury members, starting from the president, Professor François, Professor Vakaro, Professor Spyros Hadjivasiliadis, Panagiotis, and Anna Panagiotis Papadopoulos and Anna Busic, as well as my supervisors, George Kariniotakis, Ricardo Bessa, and Simon Kamal. I have some more personal acknowledgement to give, especially to my supervisors, but thank you very much for being part of this PhD defense.
Congratulations, Konstantinos. Congratulations.
Congratulations, Konstantinos.
Okay, maybe we take a picture with everybody close to the screen.
Yes. Those are the more personal ones. Okay. Thank you very much. Thank you.
Just with the advisors?
Yes.
Yeah, maybe.
Yes.
Okay.
We have Ricardo online. So.
We have Ricardo online. Okay.
Ricardo, if you can speak, so you can appear a little bit more bigger in the picture.
I can. Okay.
Perfect. Thank you very much.
Okay. Hello.
Perfect. Thank you very much.
Thank you. Congratulations again.
Yeah,
Goodbye.
congratulations.
So thanks to everybody. Thanks Alfredo, Francois, Spiros. Thanks Ricardo.
Thank you.
And have a nice weekend to everybody.
You too.
Thank you.
Okay.
Thank you.
Enjoy.
Konstantinos, now enjoy.
Bye.
Enjoy the night.
Thank you.
Okay.
Okay. Great. To stop it properly for the YouTube, not to use the video.
So, arrêtez. I take this step. Okay. Stop.